Okay, so we got 2.6 notes, day 2. Now, there's not really a whole lot that I'm covering in this lesson that I haven't already covered. It's just some more practice, and the difficulty level has gone up just a little bit. So if you find that you're able to do these problems on your own, go ahead and try them. You can fast forward to the video, see if your answers match my answers. You're good to go. Okay. So first thing, we've got an open storage bin with a square base. So it's not quite a cube, it's a rectangular prism. So I'm going to go ahead and draw a picture of this, but it is open on top, which is important when we get to volume, or not volume, but surface area. So we've got a square base. So I'm going to write X as these two sides, and I'm going to let H be the height. Okay, so it says that it is constructed from 108 square feet of material. So we know right now that the surface area is 108. Well, if I write an expression for surface area, then I can solve for H, and then I can not have an H anymore, but have this height be in terms of X as well, and I can get to the real point of this problem, which is to maximize the volume. All right, so if you think about this, the top is open. So really only the base is x squared. So I'm going to have x squared plus. Now I'm going to have 4 sides, front, back, right, and left, that are all xh, the area is. And that is going to be equal to 108. So you just now need to solve for h. And I'm going to do that. Go ahead and write the answer to this. Take as many steps, though, as you would need to solve for h here. Okay, so now we have h in terms of x. This brings us to the next point, which is we're trying to maximize volume. So in the original problem, we were probably thinking volume is x squared h, x times h. But now I can write volume in just a one variable, and this is good because my calculator likes that. It likes equations in one variable. It can find the minimum or maximum pretty easily. So I'm going to go ahead and type this into my calculator. Now, if you're going to simplify it all, the only thing really I might want to do is put parentheses around that. And then this x squared over this x. You don't have to do these things, though. Your calculator will simplify it for you. This really is only preventing you from having to type in too much. All right, so now we're going to find the max. Okay, so please follow along on your calculator. Okay, so we're going to go ahead and type in x, parenthesis, 108, minus x squared, divided by 4. One thing to note here, if you were dividing by 4x, you'd need to put that in parentheses. But since I'm just dividing by 4, I'm good. Okay, let's go to our window and let's set this manually. Let's think about what is the most x could be. Now, if surface area is 108, then volume is probably going to be somewhat close to that. So I'm thinking 10 is a pretty good max for any of the dimensions. All right, probably a lot less than that. All right, Wimax. Well, 1,000 is probably a whole lot, but maybe 200. Maybe the volume's a bit more than the surface area. It doesn't have to be perfect here. We saw in the other video that if you don't quite see the max, as long as you have a pretty good start, then you can change the window yourself and then find it. But this works. I want to find the max, so I select 4. I'm already to the left. That's good. Now I'm going to go ahead and go to the right bound. This is just like what we did in the other problem, or the other day. Okay, so now I have basically 6 and 108. So that's interesting. If you don't know what I mean by that's interesting, then you weren't really paying attention. This 6, that's not the interesting part. That means that the base is going to be 6 feet. 6 feet by 6 feet. The interesting part is this 108. This is volume. Well, surface area is also 108. That's what I meant by interesting. Now, it doesn't really ask us to list what the surface area is. It just wants the box's dimensions. So we do need to find height here. Now, you could either use the fact that the volume is 108 or the surface area is 108, or it might be even easier just to plug in your 6 right here. Now, I'm not going to show this calculation, but when you do that, you get 3. Okay, so this is the box's dimension. You would need to distinguish between what the base not necessarily length and width, but you need to show the two dimensions for the base and the height. Okay, so this next problem is totally made up, meaning that this is not taken from real life data. In fact, this really wouldn't happen this way, but it's going to practice a good concept, and we'll see in example 3 where it would actually happen. So it says, this is totally made up. However, let us believe that it takes twice as much energy for a plane to fly over water as it does over land. We are flying into a city, and we are currently 100 miles from the nearest mass of land, and the city is 250 miles down the coast from that nearest point on land. To what point should we fly in order to minimize the total energy expended in traveling to the city? So you're probably at home thinking, I have no idea how to do this. But I'm going to draw a picture that should look familiar. It's not about memorizing these problems, but noticing patterns is extremely helpful. Okay, so let's think that here's the plane to start with. Okay, and it's over water. And here is where it wants to fly along land. Now, if it flies the whole way over water, it's a shorter distance overall. However, it's all over water, which they said is twice as much energy. Now, this is the part that's made up. It's probably not twice as much energy. It's probably really close to being the same, maybe just a little bit more. But for a bird, I think that it would be more something that's actually flying. We're not taking into account wind or anything like that. It's just that, we're taking the simplest case, which is why this is totally made up. I'm admitting that. Okay, so we have this idea of we could go totally over water, but a shorter distance overall, or I could just go straight to the land. Okay, so I'm not over water for very long, not using the twice as much energy, but the distance overall is longer, so the energy overall is longer. So there's probably a happy medium. Now, remember that when we did these problems before, and we did do them before, we did a beach problem, we did a bird problem, they're going to give you some information. So like they tell us that this is 100. Okay, from where we start, we're 100 miles from land. They're also going to give you this total land distance, which is going to be 250. All right, now what you've got to do is decide where to put X. You can really put X wherever you want. The easiest place would be right there. This doesn't mean a whole lot. Well, that doesn't help if I color right on top of it. There we go. But it makes finding the other two expressions that do have significance easier. So like, for instance, this land distance along the coast is going to be 250 minus X. This water distance, we're going to use Pythagorean theorem, and we're going to do 100 squared plus X squared. Okay, so I'm actually not going to set up an equation that completely represents energy, because I don't know what that is. These expressions right here are distances. So let's just think about, if I can minimize my distance, then I can minimize my energy. All right, and that's what we're trying to do, minimize the total energy. They give us a very simple relationship. It takes twice as much energy for the water, okay? So I'm really not setting up energy. I have no idea about, it wouldn't be calories because this is a machine, but it'd probably be measured some other way. But if I can minimize distance, I can minimize energy, and it'll give me the same information that I need. So let's think about the water distance. It's this expression right here, and I need to double that, because it's kind of almost like, if it's taking twice as much energy for this plane to travel over water, it's kind of like you could say, well, it's traveling that distance twice. In terms of energy, traveling a distance twice would be the same as that thing taking twice as much energy. So we're going to kind of simplify it, but it'll work. And then the land distance, which is really on the coast, but we're counting that as land, that's just going to be once. Okay? Now once you get this set up, then this is pretty easy to solve. We've plugged things like this into our calculator before, but we were trying to find where it was an exact amount. Here we're not doing that. We're just trying to find the minimum. So I'm going to go through these steps rather quickly. If you think you know how to do this, go ahead and go on. And if you can go quicker than me, that's great. One thing you do need to know is how to set up your X max and Y max. So let's think about the most X could be. The very most would be that complete distance down there, which is 250. And our Y max is talking about a distance, the total distance. So 250 plus a little bit more, I'm going to say at most 500. Okay, but it's probably going to be less than that. Now we'll be able to see, if we can't see this minimum here, like let's say we had a blank screen, then I need to increase that max. That's what you can be looking for. Okay, so I need to go all the way to the left. Oops. Enter. Go all the way to the right. Enter. Enter for the guess. So we get this answer. You know what? I just realized I made a mistake. This is good though, for those of you listening. I looked at that and I thought, that's strange. I really don't want it. It should be in the middle. That's because I had accidentally selected maximum instead of minimum. And you can catch that mistake on your own. So really I should have selected 3 for minimum. I talked about that and then I just selected the wrong button. Easy to catch your mistake though if you're just thinking what's reasonable and what's not reasonable. I knew that that end of trace had to be in the middle of this curve. At this point, this should not be about memorization of the steps, but about just the logic of it all. All right, so we get 57.735 and 423.205. So let's go ahead and write that down, and let's interpret our answer. Because really all this work is nothing if you don't know what it means. Okay, so it says, to what point should we fly? All right, so we want to fly to this point right here. Okay, so how could you explain this? Well, you could probably explain it several different ways. I'm going to go ahead and use this number though, and I would say you want to fly 57.735 miles, because that's the units we're in. Whoops. And I'm going to write down the coast from, because I really don't know direction. This is not necessarily north, south, east, west. I really don't know. Down the coast from the point, and when I'm saying down the coast from the point, you know, directly even I kind of get caught up. We got to make sure we write this good though. Directly across I'm going to back this up a little bit. I don't like that 3. I'm going to redo that 3. So think about this. We're talking about this distance, 57.735 miles down the coast from the point, I'm going to say from the nearest point, on land from where you started. Maybe thinking, is this really necessary? Can I just not write the number? Well, you need to explain your answers. You need to interpret your answers. If you had solved this a different way and let X be something else, if you didn't explain it, you wouldn't get the credit for that. From the nearest point on land. And that's good. Okay, last problem. Very similar to the one we just did. Again, if you think you can do it, go ahead and try it on your own. Your picture will look very similar to the picture we drew in problem number 2. So it says you're standing at the edge of a slow-moving river. Now, when this is slow-moving, I want to emphasize the slow, almost like standstill. We're going to assume really no current, and you'll see why in just a second. It is 1 mile wide, all right? So we've got, well, let's just continue the problem. You know that it's dinner time because you smell the yummy hamburgers on the grill at your campsite across the river. So you've got to cross this 1 mile wide river. It says you swim at 2 miles per hour and you walk at 3 miles per hour. That makes sense. You can walk faster than you can swim. And you must first swim across the river to any point on the opposite bank. From there you can walk to the campground. So you've got to cross this river that's 1 mile wide. All right, and then here are the hamburgers. So here you are. This is where you start. And if it helps you to write this out, then definitely do it. This is where you stop. Okay, you're going to swim across the river, probably not directly, and probably not directly to the hamburgers, and probably not directly to the point across the river. Somewhere in the middle, there's a nice efficiency balance. All right. Here's where you're swimming. Here's where you're walking. Okay, it says that this point right here says you can walk to the campground, which is 2 miles from the point directly across the river from where you start your swim. So again, hopefully by now you understand where to put your X. It really just makes sense to put your X there. So then your swimming is going to be the square root of 1 squared plus x squared. And your walking distance is going to be 2 minus x. All right, it's not about memorizing this, but if it makes sense, then it'll stay with you. Not just the next week, but years to come. All right, now we've got distances, we've got speeds, but what they're really asking us to do is to minimize time, okay? So we're trying to minimize time. Now, if we start with d equals rt, we need to solve this for t. So that's going to be t equals d over r. We really need to split this up into the d over r for our swimming. And we're going to add that to the time, or the d over r it takes us to walk. So it's 2 parts. All right, so we've got t equals, okay, let's think about the distance for swimming. That's going to be this square root of 1 squared, or just 1, plus x squared, over our rate for swimming, which is 2 miles per hour. We're going to add that to the time that we spend walking, which is going to be 2 minus x over 3. Okay, and then we're going to take the minimum. All right, so let's plug this into our calculator. If you think you can do this without me, go ahead, work fast. Okay, so square root 1 plus x squared divided by 2. Make sure that divided by 2 is not within the square root. Plus, in parentheses, 2 minus x divided by 3. Again, window. Now we're talking about time here. Well, sorry, for x, we're talking about a distance that has to be less than 2 miles. Okay, but our total, our y value, is going to be time. So let's think about how many hours we think it's going to take. It's probably going to take, I would say, an hour, but let's just go ahead and put 2 hours. If it's not enough, we'll know, because we won't be able to see the minimum. But here's the minimum, and it goes right back up. So that was a good estimate. Okay, so second trace, this time I'll make sure I select minimum. I'm already to the left, enter. I go all the way to the right. Enter, enter for the guess. And here we have our numbers. Okay, so let's go ahead and write that down. 0.894 and 1.039. So it says which route will take the least amount of time. All right, so we need to say that we're going to swim. Again, we kind of have the issue of how exactly to explain it. We're going to swim 0.894 miles down, not coast, but down bank, nearest shore point. Okay, so here would be the nearest shore or bank point, and we're going to, this x right here is this value. All right, and how long will it take you? Well, it'll take you 1.039 hours. So you must really like those hamburgers to be able to swim in the brook. They must have smelled pretty good. All right, bring your questions to class. I know you have them.